Welcome back to CMOS radio frequency integrated circuits. Today's lecture, this is we are discussing fractional N frequency synthesis, and as part of fractional N frequency synthesis, we figured out that spurious frequencies are a big problem, and we needed to rethink and redesign the divider circuit, the frequency divider circuit, right. The technique we needed to revisit that. So, this is all part of the 11th module, frequency synthesis. So, this is what we were working on in the last class. We said that we are going to take a pause in our rethink and revisit of the division circuit. We need to generate some sort of a pulse width modulated signal, that is our business, and we are going to pause over there and we are going to take a look at something probably from a different course. You will find this in a course which discusses A to D conversion, analog to digital conversion. It is called a sigma delta or a delta sigma modulator. Okay. And it is not very difficult. This is basically a feedback control system, negative feedback control system, and negative feedback control systems, if the loop gain is large, then the output is equal to the input, right. That is basically the idea, that if the loop gain is large, then the output is going to be equal to the input, the error signal is going to be equal to 0. So, we are going to make this loop gain large at low frequencies and small at high frequencies. So, that at low frequencies the output is definitely equal to the input, at high frequencies the output has nothing to do with the input. Okay. So, this is our plan, and why did we put this high frequency business at all? We could have made, let us make the loop gain high at all frequencies, would that be good? No, that can't possibly be, because this quantization noise has to go somewhere. Our plant, unlike other plants, our plant over here is a plant that adds noise. It is a coarse analog to digital converter, probably a 1 bit A to D converter. In fact, in our particular case, we are going to employ a 1 bit analog to digital converter, right. And it basically introduces quantization noise. Now, this quantization noise has to go somewhere. So, that is why we made this high pass low pass business, and we said that all right, let us allow the quantization noise to go through at high frequencies, we are going to focus on the low frequencies. Now, you could build alternate systems where you could make a band pass H, band pass loop filter, and say that I will allow the quantization noise to go through at other frequencies, but only in this small band of frequencies I want my signal to go through. Fine, that is up to you, this is all yours. So, these are all different kinds of designs, right. You can design a low pass sigma delta, you can design a band pass sigma delta, etc. So, you can study all of this in your A to D conversion classes. For our purpose, let us see what happens if first of all X is digital, X is a digital signal. What are we doing in an A to D converter class? X is already digital, all right, does not matter. Let us say X is digital and it has a lot of bits in it. Okay. So, X is a number like 0.1, 0.2, 0.3. Let us say that number is represented by k bits. Then the loop filter H, capital H, is what? What is the loop filter? It is a set of adders, multipliers, delays. So, it is a digital filter. By digital I mean that it has bits as input. So, it is not just a discrete time system, it is discrete time and digital. All right. The plant that we have, what we called an A to D converter, is nothing but something that selects the MSB and throws out everything else. Okay. So, the plant is just one wire. The adder, of course, this particular adder that I have got, we have to be a little careful about this. You have got a k bit digital signal over here, you have got a 1 bit signal over here, because the plant has selected the MSB and discarded the rest. Okay. So, the plant is a 1 bit, so the feedback signal that is coming back is a 1 bit signal. So, this plus minus business, you have to be a little careful. This is the MSB, this subtraction part, you are subtracting the MSB padded with zeros. Okay. So, it is not just subtracting that 1 bit signal, it is subtracting that 1 bit signal as the most significant bit. All right. Anything else that you have to worry about? How many bits are there here? K plus 1 bits, just in case there is some overflow, there is some problem. Okay. Because the MSB, there is one, both have MSBs, right. So, that is why just to keep some space, you keep k plus 1 bits over there. Are these signed systems or unsigned? Is there a sign, or is this a signed addition, signed subtraction, or are these all unsigned numbers? What do you think? Can I work with unsigned? I could work with unsigned. Think about it. I need not have any signs at all. I can just work with unsigned numbers and do the job. Okay. So, this is my basic story, that I am going to have a k bit digital signal as my input. So, it is not just a sigma delta from your A to D converter book, it is a sigma delta suited to our needs. the output is a 1 bit signal, and the claim is that the average of the output. So, suppose H is a filter which has very high gain at DC, infinitely high gain at DC, and low gain at other frequencies. It does not matter what the gain is at other frequencies, but at DC it is a very high gain, infinitely high gain. So, typical structures would be an accumulator. What is an accumulator? It is something that looks like this. Okay. So, every clock cycle it is clocked, of course. Every clock cycle it takes the previous one and it adds and sends it out. So, you could draw it in this fashion, or I think what people would prefer is you put set of flip flops, a register which is clocked at the output of the adder. So, every clock cycle you take the previous output and add it to the new output, add it to the input, that is going to be your new output, right. So, this has a transfer function of let us say this is y, this is x, right. So, that means that these are all in the z domain. Right. So, this is the transfer function of this kind of a system. Now, if you pick y from here, you have got this. If you pick y out of this point, then you have got a delayed version of that. So, you will get z inverse by 1 minus z inverse, that is the only difference, right. Now, if I have such a scenario, then in the presence of the overall feedback, I am going to assume that there is some quantization noise because of selecting the MSB and discarding the rest, that is your quantization over there. Selected the MSB, thrown out the rest of the digits, you have quantized your number to certain two discrete possible levels. So, this is your H. Now, of course, I do not really want to call this x and y, I would rather call this E and y hat. Okay. Now, y I know is equal to h by 1 plus h times x plus 1 by 1 plus h times q, and h is 1 h is either 1 by 1 minus z inverse or z inverse by 1 minus z inverse. So, that makes it okay. Let us say h is z inverse by 1 minus z inverse. I am going to do what suits me best. Now, multiply numerator and denominator by 1 minus z inverse. So, you have got z inverse in the numerator, in the denominator you have got 1 minus z inverse plus z inverse, which is 1 times x plus again 1 minus z inverse in the numerator divided by 1 times q. So, you have got z inverse x plus 1 minus z inverse times q. What is this? It is the previous value of x plus the difference of the last two values of the quantization noise. Okay. So, that is what your output series is going to look like as a series of numbers, that is what it is going to look like. And if you want to plot the spectra of these, please go ahead, you will find that z inverse x is it is actually an all pass transfer function, it passes everything, it is just x, the previous sample of x, right, and 1 minus z inverse is a high pass function. If there is a change in quantization noise, then it is going to go through. If there is no change, it will not go through. Okay. So, let us do an example. Let us say that I want x to be 0.1, all right, x is 0.1. Instead of doing it with the binary bits, it is very complicated doing the actual system. We will just try to solve this time series, and let us just see what happens. So, here as the MSB selector part, all I am going to do is I am going to say whether the quantity is positive or negative, okay. Or let us say I quantize to 0 and 0.5, no, plus minus 0.5. So, this quantizer output is, these are the two possible values, plus 0.5 and minus 0.5. Okay. So, let us do this system. Let us say that initial quantizer output is plus 0.5. all right. And let us say that initially what I have got over here is 0.01 or 0.5, that is the initial value at the input of the quantizer. So, let us make a table. X is always 0.1, this is y, and the input to the quantizer is y hat, and this is error. So, let us say at time 0, x is irrelevant, the error signal is irrelevant, y hat is 0.5 and y is 0.5. This is where we start from. X is always 0.1. Okay. So, at time instant number 1 in the next clock cycle, you are going to find that the error is minus 0.4 . Okay. So, your new y hat is going to be the previous y plus the previous error, previous y plus the previous error is equal to previous y hat plus the previous error is equal to 0.1, and 0.1 is going to be quantized as plus 0.5, and again the error is minus 0.4. Now, the new y hat is going to be minus 0.3, and since the new y hat is minus 0.3, the new y is going to be minus 0.5, which means that my error is now going to be plus 0.6. Now, the new y hat is going to be plus 0.6 plus minus 0.3. So, plus 0.3, which means that I have got 0.5 over here, and that means that my new error is minus 0.4. If the new error is minus 0.4, old y hat is 0.3. So, the new y hat is going to be minus 0.1. That means, I am again going to get minus 0.5, and I have again got minus 0.5 over here, means that my error is plus 0.6. Okay. And then you can keep doing this. So, the new y hat is going to be plus 0.5 now, which means that my new y is going to be plus 0.5 and my error is going to be 0.4. Okay. And it is kind of going to repeat. Unless I have made some mistakes, it is going to repeat itself. What you are going to see is that if you look at 10 cycles, then 2 of them are going to be plus 0.1, minus 0.1, I am sorry, 2 of them are going to be minus 0.5, 8 of them are going to be plus 0.5. No. Okay. So, 4 of them are minus 0.5, 6 of them are plus 0.5 over 10 cycles. So, the average is going to be 0.1. Which is what you wanted to have as your average. The unfortunate part over here is that the cycle repeats itself. So, first of all, this is the basic sigma delta modulator. This is called a first order sigma delta modulator. The cycle is repeating itself, means that you are still stuck with periodicity, and as long as you are stuck with periodicity, you are going to see spurious tones at your output. So, this is still not exactly what you want. Okay. So, to break the periodicity, what one needs to do is to make this filter second order, third order, okay. And typically it is seen experimentally that that is sufficient to break the periods. What do you see as the output? The output over here is minus 0.5 sometimes, plus 0.5 sometimes, okay. I have already written down the output, so I am not going to plot it again. The output is plus 0.5 for 2 cycles, then minus 0.5 for 1 cycle, then again plus 0.5, then again minus 0.5, then again plus 0.5 for 2 more cycles, etc. Right. So, it is a pulse width modulated signal. This is a pulse width modulated signal for you, right. The width of the pulse is telling you how big the signal is. So, we are achieving the same result as before. It is just that this periodicity is not that well determined. So, for example, if I wanted instead of 0.1, if I wanted 0.3, things would be different over here, or instead of 0.1, if I wanted 1 by 3, things would be very different over here. All right. So, this periodicity also kind of depends on what the signal is. As far as the sigma delta is concerned, once again these are called spurious frequencies. This periodicity is called spurious frequencies, and sigma delta designers do not like this, which is why first order sigma delta modulators are generally frowned upon. But the good news is that as soon as you make your H, we did this first order system just for to get some understanding of how the sigma delta modulator is going to possibly work. But if you replace this first order block Z inverse by 1 minus Z inverse, if you replace it by a second order block, the good news is that this periodicity is broken. You no longer get this kind of repetitive behavior, all right. And as soon as that happens, the output spectrum of the sigma delta modulator, right now the output spectrum of this first order modulator kind of looks like this. Right, these are the spurious frequencies, but as soon as you break the periodicity by making it a higher order system, you get a better rejection over here and you get a higher slope for the quantization noise. Now, as far as we are concerned, our signal as far as we are concerned, this signal that I have got over here this x, is it a low pass signal or a high pass signal? It is a number, it is a constant number. The base station tells me go to this channel and I figure out that I have to divide by so much to go to that channel, that is that number, right. Actually the fractional part is what you are taking, the integer part is already there. Base station tells you you have to go to this channel, I figure out that my n should be 90 and I need to divide by 90.1. So, I need to figure out whether to divide by 90 or 91, according to that I will divide by 90.1. So, this x is basically something like 0.1, it is a fixed number, it is a low pass signal, it is not changing at all, or it is changing as rapidly as the base station is asking you to switch channels, which is not very fast unless you are on a plane. Right. So, as far as we are concerned, this x is a low pass signal, it is like a DC, it is a constant signal. So, really the signal to noise ratio, the signal to quantization noise ratio within the pass band can be made arbitrarily, the signal to noise ratio can be made arbitrarily large if you just keep in using integrators or accumulators as your building blocks. Okay. So, the sigma delta modulator to use is not something very fancy. An ordinary second order sigma delta modulator will do the job for you. All you have to now make sure is that you have broken the periodicity, which second order, or if you go to a third order even better, will definitely break for you. Okay. Now, why I drew this output spectrum? If this is the spectrum of the division by n plus 1 signal, what do you think is going to be the spectrum of the frequency output of the VCO? Tough question. This is the spectrum I am not going to call both control signals, right. Okay. So, the spectrum that I have drawn on the right hand side, on the left hand side is the spectrum of this control signal. Let me draw a more realistic spectrum for you. More realistic spectrum is going to look like this. Where all of this is noise, rather quantization noise, and this is your signal. Okay. This is a more realistic scenario. Now, this is the spectrum for this particular wire over here. The question is, what spectrum are you going to see at the output of the VCO, because that is the key thing, right. That is what you are trying to fix over here. What was the spectrum of this control signal earlier when we were doing pulse width modulation? What was the spectrum of the control signal when we were doing pulse width modulation? When we were doing pulse width modulation, you picked 901 cycles. Out of 901 cycles, the first 810 you were going to divide by n, so it is 0. Next 91 you are going to divide by n plus 1, so it is going to be 1, which means that every 901 cycles it is going to repeat, which means it is going to repeat at, we had 901 megahertz at the output. So, 901 cycles means it is going to repeat at a frequency of 1 megahertz. So, this control signal, this pulse width modulated signal itself is periodic with a frequency of the channel raster. Okay. So, if you looked at the spectrum of that particular signal, you would see a DC, and then at the channel raster frequencies and its harmonics, you would see impulses. And interestingly enough, the output of the VCO was also looking like that, just modulated at F naught, F output. The control voltage for the VCO looked very similar. In fact, the spectrum of the control voltage for the VCO also reflected this behavior. There was some DC and there was the fundamental at the raster frequency and its harmonics. So, that is what I have broken, that is what I have successfully broken, if I can claim that the control signal is coming from a delta sigma output which is no longer periodic. So, given that the control signal output is no longer periodic, you can expect the signal over here to be not periodic at 1 megahertz anymore, but yet you are going to do some sort of a division by n plus a fraction, okay, which means that you have done your job. Now, therefore, what do you expect at the output of the VCO? What is it that you expect at the output of the VCO? Yeah, come on. So, the answer to my question, what do you expect over here? You do not expect the channel raster to be there, fine, good. What do you expect? You expect the output of the VCO to look exactly like that, modulated at the output frequency, right. That is what is going on. You are just modulating the signal at the output frequency. So, this F out corresponds to your DC and around F out systematically you are going to see junk because of the quantization noise of this sigma delta modulator. Now tell me, how good does this sigma delta modulator have to be? It has got to be good, right. Within the loop bandwidth of your synthesizer, this is going to look like the reference within the loop bandwidth. So, the phase noise of the reference is going to be tracked by the output of the VCO, but that is only within the loop bandwidth. So, let us say the loop bandwidth is this much. So, within that loop bandwidth, the phase noise of the reference is going to be tracked by the VCO, rather the VCO phase noise is irrelevant. Outside that, the VCO phase noise kicks in. Okay. So, therefore, what should be the signal to noise ratio requirements as far as your sigma delta modulator is concerned? Tougher and tougher questions, right. So, you have to make sure that you keep this region clean enough within the loop bandwidth, right. That is where we started from, that within the loop bandwidth there was a spurious frequency, that spurious frequency went right through, that was the problem. Now, let us say that this is my loop bandwidth over here. I can have a large loop bandwidth now because I can do this division by a fraction. So, the loop bandwidth is not 1/10 of the reference frequency. The loop bandwidth is still 1/10 of the reference frequency, it is just that the reference frequency is much larger, right. So, I can have a large loop bandwidth. Now, within this loop bandwidth, whatever noise the sigma delta is producing, whether it is a discrete tone because of pulse width modulation, or whether it is quantization noise, or whether it is anything else, whatever noise the sigma delta is producing within the loop bandwidth, that noise is going to go right through my phase lock loop because it is within the loop bandwidth, and it is going to affect the performance of my system. So, I have to design my sigma delta modulator to have a certain signal to noise ratio within that loop bandwidth. Okay. So, all of these are now getting related to each other. The sigma delta modulator design now suddenly we said that it is going to be easy, it is no longer sounding that easy right, because now you have to make sure that, let us say this is my loop bandwidth over here, half of the loop bandwidth, right. Let us say this is your 1 megahertz. So, from 0 to 1 megahertz you have to make sure that there is only signal and no quantization noise. So, now you have to make a more intelligent design for the sigma delta modulator, so that no noise is produced in that region. So, you have to place zeros, for example, you have to make a higher order sigma delta modulator, so that the quantization noise is so many decibels, 100 decibels below the signal or something like that, right. So, all of this depends on what your phase noise requirements are. Now, it is really getting interlinked. So, the phase noise requirements, are the phase noise requirements of the reference oscillator. So, to meet those phase noise requirements, you should make sure that you do not add additional noise because of your mistake with the sigma delta modulator, with the division, right. The division is adding some excess noise into the system, you do not want that to happen. So, you have to keep yourself clean within the loop bandwidth, and within this loop bandwidth your requirements as far as signal to noise ratio is concerned is dictated by the phase noise requirement of your final output within that loop bandwidth, which is basically the phase noise of the crystal oscillator. So, your crystal oscillator is very clean, you have to be as clean as that, you have to make sure that you do not make it dirty, right. So, this is the scheme of things, these are all interlinked, these are all getting interlinked with each other. The sigma delta design has to be clean enough, nice enough and robust enough that you do not add additional noise. As a result, your simple addition circuit over here is definitely not going to work, you will have to work harder, you will have to place zeros, you will have to burn more power in your digital circuitry. This is digital, all digital, right. There are no analog signals in the sigma delta over there. We listed out all the different components. X is a digital number, H is a digital filter. So, basically what I am saying is that this digital filter is going to become far more complicated. You will need adders, you will need multipliers probably, hopefully you would be able to do it with just shift operations. If you can do it with just shift operations, well and good, you have saved yourself some trouble, but you will need a large number of bits because you need to make sure you are precise and so on and so forth, right. So, you are going to burn man hours, you are going to burn power in the sigma delta modulator, area and power in the sigma delta modulator, and you are going to divide by a fraction. Dividing by a fraction is going to allow you to have larger loop bandwidth. Larger loop bandwidth will allow you to have faster settling time, it will allow you to have better phase noise, unless you have dirtied the phase noise with your sigma delta modulator. Right. So, this is more or less where we are going to close this topic of frequency synthesis. We have gone into a lot of detail, we have studied phase lock loops, we did not really examine what should be the precise values of the resistors, capacitors in the phase lock loop, but we did go into a lot of detail, and if you look up the references, then all of this is discussed in a very different manner. So, that is also one reason why you come to a class and listen to a class, because the teacher explains things to you in a different way, he gives you a different perspective. So, that is what I tried to offer to you. I gave you phase lock loops from a very different perspective, from a control theory perspective. You are trying to do velocity control, this is what you have got to do. So, that is how we studied phase lock loops. Then we said that this integer n frequency synthesis is just an extension of the phase lock loop, you just divide the phase by a factor. Now, it so happens that this factor can only be an integer, so there is no problem. Then we examined where spurious frequencies came from in integer n frequency synthesis. Why is there so much importance given to the spurious frequencies? Because spurious frequencies are very annoying. If you are making a receiver and you have spurious frequencies in your synthesizer, then you might receive someone else's channel instead of yours, right. Or if you are making a transmitter and you have spurious frequencies all over, then you are transmitting at all the different channels and that is no good as far as the transmitter is concerned. So, it is very annoying, these spurious frequencies really cause havoc, and lot of times people do not pay enough attention to these, and these come in from different sides and you have problems in your radio. So, we saw that in integer n synthesis the spurious frequencies were because of non-idealities. Fractional n, it was systematic, no matter what you do you are going to get the spurious frequencies at those specific at the channel raster frequency, all right. So, that was also, that is where we said that okay, fractional synthesis is good, I want to do something like this, divide by n sometimes, divide by n plus 1 sometimes, but I should not be doing this periodically. I need to stop doing this periodically, and that is where we came up with this. We pulled up sigma delta modulators from our A to D converter book, and we modified it a little bit, because we are not really doing analog to digital conversion. We already have a digital number, we are going to create a 1-bit digital number whose average represents the original digital number. However, I want to make sure that that 1-bit digital number is not a periodic signal, that was our necessity, right, and that is what we suited our sigma delta modulator for. Then I briefly discussed the sigma delta modulator itself. We looked at the dynamics, we saw that a first order sigma delta is still going to be periodic, which is bad news. We have to make higher order modulators. Then we saw that suppose I make a higher order modulator without paying too much attention, then I am going to have phase noise problems anyway. Okay. So, you have to make the sigma delta modulator, you have to design it carefully enough, so that you do not pollute your voltage controlled oscillator output. So, the mathematics for that is very involved, we are not going to get into it, but as a rough idea you can say that if I need so many dBCs at an offset of so much frequency, so rough idea of what is the requirement on the sigma delta, right. I need phase noise less than, let us say 100 dBc per hertz at an offset of 1 megahertz. Suppose this is the requirement of phase noise of the VCO final, right. Now, the crystal oscillator is good enough for this, to give you this. Your loop bandwidth is 1 megahertz. So, you need to make sure that at 1 megahertz your sigma delta modulator gives 100 dB less noise compared to the signal. Okay. So, this kind of gives you an idea of what needs to be done. However, this is not the end of the story. You have to work on this, you have to simulate the entire dynamics, and you have to fine tune your requirements. Okay. So, with this we are going to close this lecture as well as this module. about frequency synthesis, and in the next lecture we will start a new chapter altogether, that is power amplifiers. Okay, thank you.